One announcement, the deadline to drop is Friday. And those of you guys who showed up the day before Thanksgiving, none of this probably applies to you because you are my best of the best. But if you got to get out of here before the drop deadline, think about that in the next day or two while you're eating turkey. So I have had some people ask me, like, how does that exam score or like reshuffling affect the overall grades for the class? So quickly to go on that, if you are thinking about bailing, the redistribution of the scores, right? So exam 1 was like a 61. So we're going to assume that one got de-weighted from 25% down to 15. Everyone's got their own individual weighting, so I'm just throwing this out in general. Exam 2 was a 83, so you got that one at a 30% weighting. And the final exam, shooting for 80, right? So if you think of, if I just go through and just assume that you were the average person on every exam, in the end, we're going to get like an exam average of around 77%. Right? So if the exam average is 77%, after I did this manipulating of the grades, this will be the cutoff between B and BC. Usually I shoot for 80 as this cutoff, but this semester I imagine it's going to be a few points lower. 3 points, maybe. 2 points, probably, somewhere in there, depending on how easy the final is. But if this is what it's like, the exam average will be here. This line will then shift it down a little bit. So like every grade kind of shifts down a little bit. If BC goes down 3 points, A to AB goes down 1 point, right? AB to B goes down another point. This one goes down 3 points. The D line probably goes 4 points down, right? So if you're trying to do the math, should I stay or should I go? I think it's fair to assume that if you look at the syllabus for what the grade breakdown is, it's probably going to be a couple of points lower than what's listed on the syllabus. It's not going to be like 20 points down or anything, but 2-3% for some of these grades that matter the most. Okay? Any questions on that? Okay. So those of you worried about dropping, maybe some honest reflection over Thanksgiving. Do I think I can get anywhere near the average on the final that I need to pass the class? Okay, that's done. On to the new stuff. Newton-Euler equations. So, take us back in time 1 week. In chapter 6, we found velocity and angular velocity for rigid bodies. We found acceleration and angular acceleration for rigid bodies. And we did this for all sorts of different points on a rigid body. You know, we drew a lot of blobs and we said, hey, maybe this was for point A. Maybe this was for the center of gravity. But if I knew the center of gravity, I could figure out what's happening at A. We did a little vector manipulation to get us from one point to another. It could get us all of the velocities and accelerations we need. Now it is time to put those accelerations to use. And that's what we'll do with Newton-Euler. So, another trip down memory lane. Chapter 3. Sum of forces equal mass times acceleration. Newton's second law. That's what we're going to be using again. So, think about all the steps that we had to do when we were looking at sum of forces. We had to draw free body diagrams. We had to select what coordinate system was best for us. Was that Cartesian, polar, NT? We drew kinetic diagrams for the right-hand side. We set those two figures equal to one another. That was our sum of forces equations. Solved. Well, we'll do all that same stuff again. But now we'll do it with rigid bodies. So before, if we had a box that we were pushing on as it was sliding along the ground, before we had every force acting through the center of gravity. We modeled it as a particle. Now we're going to model it as a rigid body. So we're going to take into account all the locations of these forces. So the first part, sum of forces equal mass times acceleration. Hey, that's not going to change. Sum of forces is equal to mass times acceleration at the CG. So, almost identical to what we did before. If you think of before, we modeled that body as a particle at its CG, well, and they are the same thing. But now we just have to be a little bit more careful. I'm looking for acceleration at a particular point. Maybe I know the acceleration over here at B, but I need to reference it with respect to the acceleration at the center of gravity. So that's what we'll do. So for us, we would write this. Typically, we'd say, hey, I got sum of forces in the x direction. Mass times acceleration of the CG in the x direction. I got sum of forces in y. X and y, maybe the most obvious, the easiest for us to wrap our heads around. Hey, this also works for acceleration in the radial direction, acceleration in the theta direction, acceleration in the tangential direction, acceleration in the normal direction. All we're doing is summing forces, so none of this part changes. The new thing that we will add, the sum of moments. So pretty much everything we're going to be doing in this class we've talked about is planar. So acting in the plane of the page here. Whether our coordinate system is xy, r theta, and t, it's all happening in this plane. So the out of plane direction in which the moments we're concerned with, we're looking at it in the z direction. But if you remember, think back to statics, I can't just say I'm summing moments in the z direction. I also got to pick a point. I could pick it about the CG. I could pick moments about point A. I could pick moments anywhere I wanted. So yes, we're going to sum moments about z, but at what point that we're going to use kind of matters now. There is a fancy definition in the book of what this is going to equal. So I'm just going to say point, what do my notes have? Point P for now. I'm summing moments in the z direction about point P. P could be on this body, but it doesn't have to be. P could be some spot off in space. So this is totally generic. Now, the derivation in the book, it'll use a whole bunch of things here. Talk angular momentum, blah, blah, blah. If you want to read it, it's in the appendix of the book. I don't want to do that. It takes too long. So we'll fast forward that a little bit today. I'll get back to that. Our sum of moments about the z direction is going to be equal to Ig alpha plus the vector from our point that we're interested in moments about, back to the center of gravity. I'll just call that sub g, crossed with mass times that acceleration of g. Okay, this is the monster that we're going to deal with. So what do I have here? As I'm pushing on this thing at various positions, all these forces with respect to the CG are going to cause this thing to rotate. Well, maybe not mg and n because they're going right through my CG. But the force I've drawn for F and the force I've drawn for P. So as these forces are creating moments on this body, I've got this thing twisting, right? And that's what I'm trying to figure out now. So these sum of moments are going to give us angular acceleration, alpha, multiplied by ig. This is our polar moment of inertia. Think of that as a body's resistance to rotation. If we think of sum of forces is equal to mass times acceleration, that mass, that inertial term, is it's like resistance to being accelerated. The less mass you have, the more acceleration you would have. Kind of similar here for ig. How your mass is distributed with respect to the center of gravity. If all of this mass of this box was really, really close to the center of gravity, this number would be really small. And my moments would cause a lot of angular acceleration. But if I had all my mass in this box distributed on the edges, as far away from the CG as I could, I'm taking that mass and I'm moving it away from the center of gravity, my IG is going to be bigger. I'm creating a larger inertial term that's going to resist that acceleration. So those same forces would produce less acceleration because my IG would be much bigger. Now, we also have a correction term to deal with for the fact that, hey, my point P may not be on this rigid body. And these forces can give us, or these moments can give us can lead to the acceleration of this body about point P. So we can think of this as our rotational term, and this is almost like a correction term for where we have P located. But we'll work on this all day today. This is the new part. This first piece, that's old news. So let's take a trip back to statics real quick. So we just talked about kind of what this idea of the mass moment of inertia is, this resistance to that rotational term. And we can think about it with this blob. Maybe I'll just stick to the screen for this one. For this blob shape, every little point of mass, dm, if I wanted the moment of inertia about this vertical, this z-axis, I want to integrate r squared, the distance from that axis to the little mini mass I have for this entire body. So each little incremental piece of mass, we're going to integrate that incremental mass, and its weighting factor is going to be an r squared term. So we integrate that, we get the mass moment of inertia for this body. I'm never going to ask you to do that. We'll do one in discussion next week just so you're somewhat familiar with it. But what I want you to be able to do is use a lookup table to figure out what these moments of inertia are for composite systems. So we might have a moment of inertia about some point P is equal to the moment of inertia about g plus the parallel axis theorem. The mass of that body times distance squared. So for us, we'll look at an example. I've got a rod and a disk. I've got a CG for the disk and a CG sub R for the rod and a D for the disk. But I want to figure out the moment of inertia of this system about its end here because it's pinned. And it's pinned at point P. So we have a table on our course website. All right, that's as big as it gets. But what we can look at for a composite system like this is we need to look at the table to figure out the moment of inertia of the disk about its center of gravity. Look at the table to figure out the moment of inertia of the rod about its center of gravity. And then we need to account for a parallel axis shift to get them back to point P. This is the kind of stuff that I expect you to be able to do. So if we start with the disk. Disk has radius r and a mass of m sub disk. The rod has a length of L and a mass of m sub rod. Okay? So for my disk here, I can find the one that looks like it here in the middle, over on the left side. And the moment of inertia I'm interested in is this z direction. So I of z is half m r squared. So I of CGD, the center of gravity of the disk, half mass of the disk, big R squared. For the rod, upper right corner. Again, rotating about the z direction, I of the CG of the rod is equal to 1/12 mass of the rod, L squared. All right. So now we need to shift both of these guys back to point P and add their combined effects together. So the moment of inertia about point P of just the disk would be what I have here. The moment of inertia about a CG, half m disk r squared, plus this parallel axis shift. So its mass is m disk, m sub d, and the distance is the perpendicular distance from the CG to the point we care about. So the shortest line to get me there, that's L plus R. And that term is squared. That's my d squared. And I got the same thing for the rod. I sub P of the rod, moment of inertia about its CG, 1/12 mass of the rod, L squared, plus the parallel axis shift, m, is m sub r, and my distance, L over 2, half the rod. L over 2 squared. This is the one thing I think is not on the equation sheet that's worth remembering. The moment of inertia of a rod about its endpoint, this term just goes to 1/3. I think you're smart enough to remember that. So on an exam, you could just start there. All right, the total moment of inertia about P is just the sum of these two terms. So for the disk, half m disk r squared, plus the parallel axis shift, mass disk, L plus R squared. And then the rod's term, plus 1/3 m sub r L squared. That's the kind of stuff that I'm going to expect you to do, that I can all but guarantee is going to be on your homework and the final exam. So be very comfortable doing something that you probably already learned in statics, but being able to do it again. Integrating some goofy shape, yeah, kind of useful. Not useful enough for me to make you do it. Okay. So, we've said we got this blob. In the xy plane. We've said that the sum of the moments about P is equal to Ig alpha plus R from P to G crossed with mass times acceleration of G. Okay? This is always true. We want to look at some special cases where maybe we can be a little lazy and this correction term drops out. So, actually, maybe before we do that, the slides here say something a little sneaky. Body's symmetric with respect to the plane of motion. That's going to be true for all the things that we do in here. So, what does this mean? It's like my plane of motion is this paper. Symmetric to that is like if I could look under the paper and above the paper, the thing would look the same, right? Imagine I looked at this thing from the side view. This is top. And it's rotating about z. So I'm looking down at it. Now if I look from the side, there's actually an iceberg. And here's the water. Right? So if it wasn't symmetric, when we pushed on it, we could get some rotations in the other directions, namely x or y, depending on where we pushed on this thing, if it wasn't symmetric to the plane of motion. So we're going to assume that our forces are symmetric to the plane of motion here, or in the plane of motion at its midpoint, not causing this thing to rotate or twirl in these other two directions. We're only focused on the rotation about z, right? So if I was pushing here, causing it to rotate about z. I don't want to concern myself with that just yet. We'll do that to you in EMA 542. But looking back at this now, how can I make this term go to 0? What do we need to do to make this guy fall away? There's a couple special cases that we can look at. Case 1. P is G, or CG, the center of gravity. If we're taking our moments about P, and P is co-located with our center of gravity, I've got an R vector from P to G, some point to itself. That's a pretty short vector. This piece falls out, 0. So the R's gone. This gives me R from G to G, right? That's 0. Next way, the acceleration of G is equal to 0. All right, that's actually more common than you think. Maybe it's pinned at G. Or maybe it moves with a constant velocity, so it has no acceleration. Right? Anything that's going to make the acceleration term fall out. This guy goes to 0, that cross product is 0. The last one, maybe more of a special case. The acceleration of g and our vector are parallel. So because it's a cross product, the cross product between two parallel vectors is 0. So in this case, maybe if p is already right here, this would be my r from p to g. And maybe my acceleration was in that direction. If that's the case, that's 3. So these special cases can make your life a little bit easier. Some things you don't have much control over. But you don't know if you don't have control whether the acceleration of gravity is 0. Right? But you do have control over this first one. This first one is the points at which you've decided to take moments about. If you decide to take moments about the CG, that's what this is saying. So this is take sum of moments about CG. If you ever decide that, then immediately you've made life easy. Get out of there. Of course, now it's like super dark too. Okay. So, special case. If you want to make sure you don't get it wrong, go with the full blown. You don't always need to, though. Hey, look at that. One more special case to look at. We've got our blob. There's our CG. If we want to take our sum of moments with respect to a point on the rigid body, so point O is on the rigid body. If this is the case, then we can rewrite our sum of moments. Sum of moments about O is equal to I sub O times alpha plus R from O to G crossed with mass times the acceleration of O. You think that looks pretty darn similar. And it is. Now what did we start with? We started with the sum of moments about P is equal to I, this is different, sub G instead of O, plus my vector, that's really no different, I just swapped O for P, cross with mass times acceleration of G. So where we get some bang for our buck here is that now I'm not looking at acceleration at the CG, I'm looking at acceleration at point O. I'm looking at my moment of inertia with respect to point O. So when is this useful? This is pretty useful in the event that your body is pinned at O. If you're pinned at O, what does that do? This second term will drop out, right? So the sum of moments about O is I sub O times alpha. You could come up with some other cases that also make this go to 0. Acceleration of O is 0. That's kind of what we talked about with this pin. But this is going to be kind of the most common way that we use that. And we didn't do any black magic to get here. All we did is we started with our expression here. Then we swapped O is equal to P, right? Nothing too sneaky. And then we did have to make one more little bit of work here. We said that I sub O is equal to IG plus the parallel access theorem to get me from G to O. This is my R to O from G, right? Hey, that's this guy. And that's my shift. All right. I got 20 minutes left. I don't have time for this. If I would take this, actually solve this for IG, so scoot this around. Plug it in here. And I just swap these points P for point O. You would see that this guy would fall out. So as long as you're comfortable doing a cross product or two, you could get there. I want to get on to the good stuff, though, so I want to keep that going. So a little bit of trust, that's what it would break down to. So we've been doing free body diagrams and kinetic diagrams for bodies modeled as particles. But now that we're doing rigid bodies, the kinetic diagram part actually matters. It's pretty simple for a particle. All you had to do was tell me, hey, am I using r theta, x, y, and t? And that was it. All the mass time acceleration terms went from the CG. Now, we've got to be a little sneakier. So, FBD is equal to the kinetic diagram, right? Those are the exact same shape. So your FBD is going to have your external forces. I've got F1, F2. I got some moment. So no different. You guys just look at the picture, figure out what the external forces are, and have those for your free body diagram. The kinetic diagram side, this has become more interesting now. So, remember, sum of forces equaled mass times acceleration at the CG. The CG. So for our sum of forces, I would still want mass times acceleration x, mass times acceleration y. And this is assuming this is my CG. You could have r theta, you could have nt, but you're going to have these guys attached to your center of gravity. Sum of moments, Ig alpha plus r from G to P crossed with mass times acceleration at G. All right. This is the one we got to be more careful. Where is the point P that I want to sum my moments about? You know, if it's over here, I make sure to draw that in my kinetic diagram. Because this, for me, helps me remember, yeah, don't forget about that second term. So I draw that in my kinetic diagram. The first part, I could put in as Ig alpha And I went from little g to big G. Sorry about that. So that's this term. And then I've got an R from G to P. Cross with mass times the acceleration at G. Hey, what's the acceleration at G? You've kind of already got those two pieces, right? But it's a vector. It's both pieces of that. So when I'm drawing this for the kinetic diagram side, now it's time to bring in all these little pieces that we might forget about. If P is located at the CG, wonderful. This term's going to fall away. You're not going to need this R vector or P, right? But in general, you're going to have these terms. So what did we just talk about? We had a pinpoint O on the body. Yeah?
Does it matter what direction the R vector is? Because on the slide it's going from P to G to G to P.
Yeah. Yes. It does matter the direction because your cross product is going to be messed up. So this, I think that every other time today I've written it the right way. P to G. So thanks. Let's fix this, everybody. G to P, P to G, arrow going up, from P to G. Thank you. I want everyone getting their cross products messed up. All right. I didn't screw that up. Now we're on to something else. So if we have a point pinned on the body, I've got some camshaft here. And let's say it's pinned over here at point O. So my free body diagram, I wouldn't necessarily draw this little pinned action, but I want to do it so we know it's pinned. I would have O sub x, O sub y as my reactions. I would have a mg coming down. If I've got gravity out in this system, I could have a moment working on this thing. Right? So for a point O on our body, we had, if it was pinned, sum of moments about point O equal to I sub O, alpha, plus R, no, I don't want to screw this up, from O to G, cross with mass times the acceleration now of point O. So if this was our case, and point O happened to be pinned, that acceleration term we don't need to worry about. So if we draw our kinetic diagram side, what do I have? I've got sum of forces, so I still need mass times acceleration in the x, mass times acceleration in the y. And again, that could be r theta, that could be nt. And then, for my sum of moments, I need I sub O times alpha. So here, over in the corner is point O. So to remind myself for this kinetic diagram, I don't write Ig, right? I sub O times alpha. If you wanted, you could say Ig and then put a vector telling yourself, hey, I need to move from G to O. I need a parallel axis shift to get me over there. So writing our free body diagrams and our kinetic diagrams now has become more important. Those of you guys who printed out the slides, this is just a repeat, except to be sneaky. It's with point O on the body instead of point P on the body instead of point O. So this slide should have been deleted. Okay, that was section 7.1. Section 7.2 is a simplified case of that. Translation only. So, translation. This body's sliding, but not rotating, right? So, sum of forces for our translational terms still equal mass times acceleration at the CG. But I've got alpha is equal to 0. Translating only, no rotations. So if this is our case for translation only, you think, hey, the sum of moments equals 0. That's an equation, looks really easy. I don't want to have to do anything about that. But I think just because the sum of moments equals 0 doesn't mean there's no information contained in that equation, right? You spent the whole semester in statics where sum of moments for everything were equal to 0. But you still did it. So this equation for moments, you still got to look at it because it might tell you the balancing between two forces. And it just won't have any rotations. So we'll look at one of those. So our example problem, I've got a pipe of mass 800 kilograms and is being towed behind a truck. So that's what this big disc is behind this truck. Our angle theta down here is 30 degrees. And we're looking to determine the acceleration of the truck and the tension in the cable. We're given the coefficient of friction between the pipe and the ground is 0.1. All right. So as this thing is sliding, the truck is towing it. We're going to assume that that disc isn't spinning. We're going to assume that for this configuration, when theta is equal to 30 degrees, the truck has some constant acceleration, which is holding it in this configuration, not rotating the disc. So we're going to start all these problems the same way. We're going to write our free body diagrams, a kinetic diagram, sum of forces, sum of moments, solve it. So if we can do this first part, we're going to be in good shape. So our mass, 800 kilograms. Theta, 30 degrees. Friction coefficient, 0.1. Our radius, 0.4 meters. Well, I'm trying to find acceleration in the x direction, because I'm going around the horizontal, and the tension in the cable. So, FBD time. As this pipe is being dragged along, it's going to have an external mass times gravity. It's going to have a normal force from the ground. It's being dragged to my right, so it's going to have friction opposing that motion. And at 30 degrees, it's going to have a tension, but this actually goes off at 45 degrees. All right, free body diagram, done. Kinetic diagram. Mass times acceleration in x. Mass times acceleration in y. Then you got choices. Where you take your moments about kind of finishes off this diagram. I can take moments anywhere I want. But we think One way to simplify that set of equations for us was to take moments about the CG. I could take them about point C here at the bottom. I could take them about this application of point T. But if I look at I sub G, alpha, that'll help eliminate one term in the moment equation for me. By doing this, I do have to take moments about G. So I'll have a contribution of moments from my frictional force. I'll have a contribution to the moment from this tension that I'll have to eventually contend with. But step one, free body diagram, kinetic diagram. So x direction minus the force of friction plus tension. And I just have this piece. I got the cosine 45 leg of that. Equal to my kinetic diagram side, mass times acceleration in the x. All right, again for y. Normal going up, mg coming down, tension going up. Now it's going up at sine 45. Mass times acceleration in the y. All right, last one. Sum of moments about g. Positive counterclockwise. Take a look. N and mg work through my center of gravity. So those will create no moment. Force of friction, though, not so lucky. So my force of friction, that's going to create a moment in the minus z direction. So we got minus the force of friction. Its moment arm is the radius. Plus the moment created by this tension. So if you take a look at the figure and you're really careful, you'll see that this tension doesn't operate through our CG. So there is some little perpendicular distance here. So if you wanted, you could just set that up and do some trigonometry. Or you can say, hey, that moment is r cross f. So our r is our r from our center of gravity to point A crossed with f. And in this case, that's t. And that's going to be equal to moment of inertia about g times alpha. But in this case, alpha is equal to 0. So we explore what we have here. We know that the force of friction for sliding is mu k times n. We got mu k, n, not so lucky. Ax, I'm still trying to get. T, I'm trying to get. For my y equation, my acceleration in the y direction is going to be 0 if this guy is being pulled across a flat surface. It's not accelerating in the up and down. So this goes to 0. So for my y direction, I don't know n, and I don't know t. And then in my moments direction, what do I got here? My force of friction, which is still mu k n, and t. So 3 equations, 1, 2, 3 unknowns. So first thing, you can solve the y equation to get rid of, or get t in terms of n, and then plug that in to solve. T is equal to 2,381.6 newtons. N 6,164. And acceleration in the x direction, 1.33 meters per second squared. Okay. The actual work is already posted on Canvas, so we'll just jump to the end. All right, enjoy your break. I'll see you guys in a week.